We are going to learn about a bizarre mathematical function known as the Dirac delta function. Before we begin, let us consider a mathematical function which is also a vector and shown as in this figure. We see that the length of the arrow changes as we go away from the center. So this indicates that the strength of this field decreases as we go away from the origin. Let us represent this mathematically as P equal to r hat over r square. We see that at every location, vector v is directed radially outward, and it has a large positive divergence. With that in mind, let us calculate the divergence of the vector function del dot v. In spherical polar coordinates, this is equal to 1 over r square dou over dou r square dr. And this is equal to 1 over r square dou over dou r square times 1 over r square. And this is equal to 1 over r square dou over dou r of 1, which is equal to 0. And the plot thickens when we apply the divergence theorem. According to the divergence theorem, we have volume integral of del dot v d tau equal to surface integral of v dot. Now, if you are integrating over a surface having radius r centered at the origin, then the right hand side of this equation is surface integral p dot dA is equal to integral 1 over r square r hat dot r square sine theta d theta d phi times r hat. And this is equal to 0 to pi sine theta d theta times integral 0 to 2 pi d phi. And this is equal to, let us call this as equation number 1, this as equation. Now, when we calculate the volume integral del dot v d tau, this is equal to, so from equation number 1, it may seem that the function does not have a divergence at all. In the first look, it may seem that the divergence theorem has a discrepancy. But this is not the case. The mismatch that seems in equation number 2 and 3 is entirely due to the functional form of v. From an inspection of the nature of the function, we see that it blows up as r tend to infinity. That means that when we take the limit r tend to 0, vr, this is equal to limit r tend to 0, 1 over r square, and this is equal to infinite. What happens when r tend to infinite? In this case, when we take the limit r tend to infinite of vr, this will be equal to limit r tend to infinite 1 over r square, and this is equal to, that means that the function blows up at the origin. This indicates that del dot v has a bizarre property that it vanishes everywhere except one point, which is r equal to 0. At r equal to 0, we should have the volume integral del dot v d tau equal to 4 pi for any sphere, no matter how small. And no ordinary functions behave like this. What we have stumbled on is a mathematical object known to physicists as the Dirac delta function. It arises in many branches of theoretical physics. We'll now try to understand the mathematical form of a one-dimensional Dirac delta function. The one-dimensional Dirac delta function delta x can be picturized as an infinitely high, infinitesimally narrow spike with area equal to 1. That means that we mathematically define a Dirac delta function as delta x, which is equal to 0 if x is not equal to 0. And the value of the function will be infinite if x equal to 0. Also, when we take the area under the curve within the limits minus infinity to plus infinity, this will be equal to 1. Technically, the Dirac delta function is not a function at all, since its value is not finite at x equal to 0. This point, what you see, is x equal to 0. In mathematical literature, it is known as a generalized function or distribution. Now let us consider an ordinary function fx. Fx is not a delta function. Now, when we take the product of fx and delta x, this will be equal to 0 everywhere except at x equal to 0. From this observation, it follows that fx delta x is equal to value of the function at x equal to 0 multiplied by delta x. This is because the product is 0 anywhere except at x equal to 0. And therefore, we replace fx by the value it assumes at the origin. In particular, when we take the integration from the limit minus infinity to plus infinity, this will be equal to f0 times minus infinity to plus infinity delta x dx. And this will be equal to f0 times 1, and this integral becomes f0. What this equation indicates is that under an integral, the delta function picks out the value of fx at x equal to 0. Note that the integral need not run from minus infinity to plus infinity. It is sufficient that the domain extend across the delta function from minus e to plus e. That is, the domain where the function is defined should enclose the delta function also. So in this case, when we calculate fx times delta x, this will be equal to f of 0. But in the second case that I have drawn here, the extent of integration of the function is outside the delta function. In this case, when we calculate fx times delta x, this will be equal to. In the previous case, what we have seen, the center of the delta function was at x equal to 0. But we can very well shift the spike from x equal to 0 to some point x equal to a. In this case, we'll define the delta function as x minus a, and this will be equal to 0 if x not equal to a. And this will be equal to infinite if x equal to a. And also, when we integrate the function from minus infinity to plus infinity, the value of the function will be equal to. And also, when we multiply a mathematical function other than a delta function fx with a delta function, this will be equal to f of a times delta of x minus a. And when we integrate the function within the domain minus infinity to plus infinity, this will be equal to f of a. This is how we define a one-dimensional Dirac delta function. We'll now try to evaluate the integral 0 to 3 x cube delta x minus 2 dx. An inspection of this integral reveals that the delta function is centered at x equal to 2. That means that the delta function picks out the value of x cube at the point x equal to 2, so that the integral becomes 2 raised to 3, which is equal to 8. Now let us try to calculate the integral for the domain from 0 to 1. In this case, this will be equal to 0. Why? Because the delta function is defined at x equal to 2, and the function x cube is defined from x equal to 0 to x equal to 1, so that the domain of integration does not include the delta function. Evaluate the integral 2 to 6 x to the power of 6 3x square minus 2x minus 1 delta x minus 3 dx. Our first inspection will be to see where the delta function has been defined. In this case, it has been defined at x equal to 3. And now we see that the extent of integration is from 2 to 6. So we understand that this function covers the delta function in its domain. And now we have minus infinity to plus infinity fx delta x minus a dx equal to f of a. Therefore, when we calculate f of a, this will be equal to 3 times 3 square minus 2 times 3 minus 1. And this is 27 minus 6 minus 1, and this is equal to. Evaluate the integral minus infinity to plus infinity natural logarithm of x plus 3 delta x plus 2. In this case, fx is equal to natural logarithm of x plus 3 delta x plus 2. As before, when we calculate f of a, which is f of minus 2, this is equal to natural logarithm of minus 2 plus 3, and this is equal to natural logarithm of 1, and this is equal to 0. Another important property of delta function is that delta of kx is equal to 1 over modulus of k times delta x. To prove this, consider an arbitrary test function fx. Now we consider the integral of this function from minus infinity to plus infinity multiplied by the delta function kx. To calculate this integral, what we first do is to change the variable and substitute y as equal to kx. And this gives x equal to y over k and dx equal to dy over k. We will now have to define the integration limits. If k is positive, x equal to infinity implies y equal to infinite. This indicates that the integration runs from minus infinity to plus infinity. When k is negative, when x is equal to negative infinite, then this implies that y is equal to plus infinite. And x equal to plus infinite implies that y equal to minus infinite. When we change the variable, this integration, that is minus infinity to plus infinity, fx delta of kx dx becomes minus or plus integral plus infinity to minus infinity f of y over k delta y dy over k. We can change the sign of the integration if we can flip the integration limits. So this means that this is equal to plus or minus infinity to plus infinity f of y over k delta y dy over k. When we use the fundamental property of the delta function, this integration becomes plus or minus 1 over k f of 0. We see from this expression that when k is negative, negative times negative is positive and the value of the function is positive. When k is positive, positive multiplied by positive is positive and therefore the function is again positive f0. And therefore we can write this as 1 over modulus of k times f0. Or under the integral sign, the delta kx serves the same purpose as 1 over modulus k delta x. So this indicates that delta of kx is equal to 1 over modulus k times delta x.